Good morning. This is our last lesson in our little mini unit on exponentials. So it's a very, very short unit on logs and exponentials. It's covering what you need to know for your EOC. Then we're going to jump over and do probability and statistics. And after the EOC, we're going to go back to the exponentials and logs and really cover those in more detail. You will need more exponents and logs for pre-calculus and for college algebra, depending on the direction you're heading, but it's not assessed on your EOC. So we're at the time of the year where we need to just kind of make decisions about the timing of things. So what I'm going to do with this lesson is actually do a quick reteach and summary of what we already know about exponential equations. And then I'm going to introduce something called the natural exponential. The deal with the natural exponential is going to look a little different, but absolutely nothing changes in terms of any of the principles or concepts that we've covered so far. So we've been looking in the last several lessons at exponential equations. And remember that an exponential equation is an equation where the variable is in the exponent. And we've looked at two strategies for solving them. So two strategies. One of them is writing both sides as a power of the same base. And as an example of that, we're going to look at 5 to the x plus 1 is equal to the square root of 5. Now, we didn't really look at any that had this form when we covered it, but my college algebra kids definitely see stuff like this. And we have covered enough that you can follow what's happening here. So we have 5 to the x plus 1, and then on the other side, we have the square root of 5. Now, in order to use this strategy, you need to remember this fact. You need to remember that the square root of 5 is 5 to the 1/2 power. So everything that we have covered, like, you're expected to remember it. So that's why you need to study, taking shortcuts, using photo math to do your homework and stuff. It doesn't pay off in the long run. It puts like a Band-Aid on a mortal wound. You need to go and address the actual concepts and the material you're supposed to be learning. Once you do that, once you have those bases the same, then you can set the exponents equal. And so we would have x plus 1 is equal to 1/2. And try to avoid saying stuff like the bases disappear. Maybe you could say the 5s cancel out. And just say we set the exponents equal is the best way to say it. Now, you can probably do this in your head. You're going to solve this by subtracting 1 from both sides. And so 1/2 minus 1 would give you negative 1/2. If you're uncomfortable doing that, you could do something like this. So we'll just kind of address a few things. You could change the 1/2 over to a decimal. Okay, so you could use 0.5 and do it that way. Okay, and then you'd end up with negative 0.5. Which I hope you recognize is the same thing. You can also use your calculator. So your calculator, if you have a scientific calculator, will subtract and operate with your fractions. And so you just need to know how to do it on your model of calculator. The calculators are all a little bit different. So if you would like help on figuring out how to use your calculator to do it, I'd be more than happy to show you. Now, the second strategy was using a logarithm. So we're going to look at an example of that. If we have negative 2 times 6 to the 2x minus 1 is equal to negative 10. And we went through this in the last lesson. So your first step would be to isolate the exponential. And you want to recognize that the exponential here is 6 to the 2x minus 1. You do not want to do negative 2 times 6 because that is a order of operations mistake. You can't do multiplication until you deal with the exponent. You have to deal with that 2x minus 1 first. And so we need to basically get rid of the multiplication because we can't do the multiplication. The way we would get rid of it is through division. So we'll divide both sides by negative 2, and that'll give us 6 to the 2x minus 1 is equal to positive 5. Then we change it over to a logarithm. So this would be log base 6 of 5 is equal to 2x minus 1. And then we'll throw that into our calculator, however your calculator does it. So that'll be the log of the attic divided by the log of the basement. And that gives us a decimal. It gives us 0.8982. And once you have that decimal there, then you engage your Algebra 1 skills for just solving for x. So we'll add 1 to both sides, and that'll give us 1.8982 equals 2x. And divide both sides by 2. That's probably a lost cause, trying to 2. And we'll get x is equal to 0.9491. Just don't quite have enough space to do that. And that is a review of the last 2 or 3 class sessions where we've gone through the different strategies. So if you've missed one of those classes or more and you haven't watched the videos to make it up, which you should, that is what I expect you to do, is watch the videos to make up the material that you miss. Then what we got there was what's called a reteach. It's embedding like that review and that instruction and the modeling back into the lesson again to keep it fresh. Now there's one more situation that we really need to look at before we leave exponents behind for a little bit, and that is something called a natural exponential, and we'll put a little slash there, and logs. So natural, we'll pluralize that, natural exponentials and logs. Now to do that, we need to look at a special number called e. And you may have noticed in your studies of math up to this point that you very, very rarely will see a lowercase e as a variable. Once in a while, it does pop up. You might see an e used as a variable, but very rarely. And the reason that you almost never see a lowercase e used as a variable is because it's actually shorthand for a number. In my college algebra classes, we look at where the number e comes from, and it comes from taking what's called a limit. So those of you that go onto pre-calculus at some point, like usually towards the end of pre-cal, you will study something called a limit, which is basically asking yourself what happens as x gets bigger and bigger and bigger and bigger and bigger. And you study this idea. Now, we're not going to go into the idea of limits and where the number comes from. For you guys, I'm going to tell you this. E is a number like pi that occurs in nature. And so you're familiar with other numbers that occur in nature. The number pi is derived by looking at the circumference and the diameter of a circle. And it happens that with any circle ever, if you measure the circumference of the circle and you measure the diameter of the circle and you take the ratio is always the same. And then that number turns up in pretty much anything that has to do with circles. E is a similar number. It's a number that occurs from doing a particular process, and then it turns up in all kinds of places in math. It's going to turn up when you deal with money. It's going to turn up in all kinds of science applications. So if you're wondering what is E about equal to, it's about equal to 2.71828. And it does keep going. So that's about what E is equal to. It's between 2 and 3. It's closer to 3. So you know that pi is like 3.14159, and it keeps going. E is 2.7828, and then it also keeps going. And just like we don't normally write 3.14159 for pi, we often use the pi symbol. When we're dealing with E, we usually use the lowercase e. Now, how does that relate to anything? When e is used as the base of a logarithm, it gets its own symbol. So let's say, for example, you had e to the x power equals 5. Okay. Now remember, e is just a number, so you don't want to let that freak you out. It's not two variables in there. E is a number. You could say 2.718, to the x power is equal to 5. Like, you could say that, but don't, okay? Nobody does that, and you're not going to pioneer it by being the first person to ever do it. But you want to keep that in the back of your head. Like, that's what it is. It's just kind of a yucky looking number for the base, and it's got its own symbol. When you go to change that to a logarithm, you will have log base e of 5 is equal to x, and log base e actually gets its own symbol. So log base e gets its own symbol. That's a y right there. It gets its own symbol. That is log base e is equal to ln. So this is called a natural exponential when the base is an e, and this is called a natural log. This is an L. It is not an I. Not an I, not an I, not an I. It floors me how I can emphasize this, and even how it should make sense. It's a logarithm. L is for logarithm. The N is for the natural. And so logarithm starts with L, and every year there are students that will put an I there. And I think the reason for that is when you're typing, a lowercase l looks like a capital I in a lot of the different fonts that we use. And so students will see that and they'll see a capital I. It's not an I. It's an L. If you start giving me I's, I'm going to yell at you in my comments, okay, that it's not an I, and you need to come back and you need to watch this video again where you know what, we're going to put it in, we're going to circle it in red, we're going to star it, okay, and for those of you that have never made this mistake and never will, you're probably wondering why I'm emphasizing it so much. It's because this happens all the time. It even happens with students that are in college algebra, students that are in pre-calculus, that will habitually and chronically refer to this as an I, and I have no idea why. Now, here's the good news. Okay, we have this new symbol, like just ln is for log base e. Here is the best news you had all day. Everything else stays the same. Literally everything else that you've learned about exponents and that you've learned about logs stays exactly the same. So I have two examples to take you through solving equations with natural exponentials. And truthfully, as you move past algebra 2 in your math, when you see exponential equations, they are often going to be natural exponential equations. When I say this turns up in nature, and it's going to turn up in like your money problems, those of you that take financial algebra, you're going to see E pop up in the money formulas. In your science classes, you are going to see natural exponentials. So we're going to do two examples. You're probably going to see this outside of this class. Not all of you will, but a lot of you will. So we have example 4 e to the 2x plus 2 is equal to 16. So literally everything, that's huge. There we go. That's a little bit better. I keep running out of space writing these. It's probably because I'm writing the problem super huge. So for e to the 2x plus 2 equals 16, everything you know about solving exponential equations is exactly the same, which is awesome because math is consistent. And if you learn the principles and you learn the properties, you will be able to solve all kinds of stuff without a teacher having to show you how to solve it. So step number 1 for solving any kind of exponential equation is you want to isolate the exponential. It's important to recognize what the exponential is. The exponential is the base and the exponent with the variable that goes with it. So in this problem, that right there that I circled, that's your exponential, e to the 2x. I'm going to pause a moment and let you process what I just said there. Okay, now the reason why that's important is because your first step is to isolate that exponential, which means the 4 and the 2 we don't want there. And so just like you would be solving a linear equation, you would undo the adding and subtracting first, and then you'd undo the multiplication. That's how it's going to work for this problem. So we're going to subtract 2 from both sides, and we'll have 4e to the 2x is equal to 14. And then we're going to divide both sides by 4 because that is multiplication. It's multiplication, and you undo multiplication with division. None of those properties or principles change. So we end up with e to the 2x. Now, you can leave that as a fraction. You can simplify the fraction. You can change it to a decimal. I'm going to go ahead and change it over to a decimal. So that's 3.5. Now we change this over to a log. And nothing changes. Log base e of 3.5 is equal to 2x. Now, remember what I just said. Log base e gets its own symbol, which is ln. And so when you write it as log base e, you're going to replace that with an ln. This step right here, I want you to skip as soon as you are comfortable skipping it. Okay? Because nobody really writes log base e. Okay, nobody writes that. I think everybody would understand what it is, but nobody writes it. I'm going to write it for these first couple of problems because I want to emphasize how the concepts are the same and then emphasize what the ln is. But in reality, I would not write that out. Like I wouldn't write it out as log base e. So, but I don't want you skipping it until you're comfortable skipping it and you're comfortable just kind of jumping over that step there. Okay, now here's the good news is, let's talk about exact answers. I did mention that in the last lesson that we talk about exact answers. So there's like 2 different ways that you could approach this. When we did the last lesson, we actually went to evaluate the log. Now, ln has its own button on your calculator. So I mentioned that your calculator does 2 kinds of logs. It does that common log, which is the log base 10, which is the LOG key. But near your LOG key, there's another key that says ln, and it's like to the left, to the right, above it, below it. They're always right near each other on your calculator. There is a button that says ln, and so you don't have to use the change of base because your calculator is equipped to do this. And you could just punch in ln of 3.5, and you would get 1.2528. And then divide both sides by 2, and you would get 0.6264. Okay? Whoops. All right. So 0. Now, sometimes you will be asked for something called the exact answer. So what I'm going to do is I'm actually going to copy the ink of this problem onto the next page, and I'm going to erase some of the work. So we are going to, let's see, duplicate page and ink. Page 6, page 7. Awesome. What that does is that allows me to erase something without actually permanently altering it, so I can still go back and look at the other work. So when you do the natural log of 3.5, the actual number my calculator gave me was 1.125276298. Well, clearly I didn't want to write all of that out. And so the moment I did that here, I rounded. And so I have what's called an approximate answer. Sometimes you are asked for an exact answer. If that happens, all you do is you just don't evaluate the good grief, the logarithm on your calculator. And so you would just skip straight to divide by 2. And so your answer would be x is equal to the natural log of 3.5 over 2. It's actually easier because it avoids a calculator step. It's one step less that you have to do, and yet students do kind of get tripped over the fact that your answer has an ln in it. So this answer is what's called an approximate answer because of the rounding. This answer is what is called an exact answer because you have not rounded anything in it. You should be able to do both. And I was doing this, I mentioned I'm doing the same material with my college algebra class. And so I was doing yesterday an assignment on the computer because they have to do all their homework on the computer in a program. It's similar to Math Excel, but anyway, the answers frequently said give the exact answer and then give the approximate answer rounded to so many decimal places, and so the students have to demonstrate both skills. I'll do the next example the same way. I'll demonstrate both skills. So our next example is e to the x over 3 plus 3 is equal to 15. Don't let the fraction freak you out. Math is consistent. And as we go through this, I want you to pay attention to how I think through it. It's not about memorizing a bunch of steps. Like if you see this, then do this. You want to train yourself how to think, not what to think. Like a good teacher does not tell you what to think. A good teacher will teach you how to think, how to process stuff. And then you do your own thinking for yourself. So step number 1 is you want to isolate the exponential. We want to make sure that we can recognize the exponential for what it is. So this is e to the x over 3. To isolate that, I need to subtract that 3 from both sides. So e to the x over 3 is equal to 12. Next step is to change it over to a logarithm. Now, I am going to do this step. Log base e of 12 is equal to x over 3, but log base e does get its own symbol, which is your ln. Skip that as soon as you're comfortable. Don't skip it until you're comfortable and you're confident skipping it. Okay, and you write log base e for as long as you need to write it to get it like locked into your head what the ln actually means. But as soon as you're comfortable with it, like go ahead and drop that. Now, if I'm asked to do the approximate solution to this, then I will grab my calculator and I will put into my calculator the ln of 12, and I have my own, the own button to do that. And that gives me 2.4849. Now that is an approximation that's rounded. I'm looking at my calculator right now. It says 2.48490665, and even that is rounded because my calculator only holds so many decimals. So that is the approximation step. Now, don't freak out about the x over 3. Don't tell me I don't know how to do that. So here's the question you're going to ask yourself. I'm going to guide you through the how. What is the 3 doing to the x? And how do you undo that? And that's what you always want to ask yourself when you're solving an equation. What is happening? And how do I undo it? So when I asked, what is the 3 doing to the x? You should have answered in your head, dividing it. And then the follow-up question, how do you undo division? Multiplication. And that's how you determine what you're going to do to solve this problem. So we are going to multiply the right-hand side by 3, and we multiply the left-hand side by 3. And that gives us 7.4547 is equal to x. That is your approximate solution to the problem. Okay, I'm going to go. Whoops, I hit the wrong button and it paused the recording. We're going to duplicate the page and the ink, and we're going to go ahead and erase this. All right, new page. And if you are asked for the exact answer, then you are not going to evaluate the natural log of 12 because that's where the approximation is happening, and you just jump over to the next step, which is to solve for x, and you would ask yourself the same question. So what is the 3 doing to the x? It's dividing it. And how do I undo that? I multiply. Now you do want to be a little bit careful here. So that is 3 natural log of 12, and that is your exact answer. So you have your approximate answer and then you have your exact answer. And you can do the same thing with logs of other bases. You just skip over the step where you evaluate the log. Now, I do want to address one more thing before I release you guys to do some practice work. When you have this, you have the natural log of 12 is equal to x over 3, and then you multiply the 3 on both sides. Try not to multiply it on the right hand side, because the 3 is not, you're not taking the log of the 3. You're taking the log of the 12, and then you're going to multiply that answer by 3. You can see that a little bit more clearly here. You take, you take the log of the 12, and then you want to multiply that answer by 3. If you get careless and you do the 12 times 3 is 36, okay, so let me clearly label this as wrong, okay, and so you do that, and then you do the natural log of 36, it's going to give you 3.5835, which is the wrong answer. Okay, so make sure that when you're multiplying both sides that you are retaining your order of operations there, which is do the log first and then do the multiplication. If you multiply first and do 12 times 3 to get 36 and then do the log, so much comes back to order of operations. You think order of operations, that was 6th grade. Please excuse my dear Aunt Sally. And then order of operations keeps coming up because it's easy to get stuff wrong. So how should you practice with this? Let's get a little practice. So here are 3 practice problems. E to the x minus 2 is equal to 12. And the answer to that is 4.4849. That is so you can check your work. 2e to the negative x. Ooh, craziness. But you know what? Math is consistent. And the answer to that is x is negative 2.3026. And the third one is e to the 3x plus 5 is equal to 15. And your answer to that one should be 0.7675. So I'm going to let you guys loose to practice. Again, I'm giving you the answers, not so that you can just copy down the answers and give them back to me, because that's really silly. I'm giving you the answers so that you can know if you're carrying out the steps to the problems correctly. And that wraps up our mini unit on exponentials and logs. I hope you've enjoyed it as much as I have.